So what we're going to do today is go on to chapter 17, and we're going to look at electric charge. Okay, electric charge. And this is a general introduction to electricity and magnetism, which is the topic that we're going to study for mostly the remainder of the year. Okay, there's going to be about 3 or 4 chapters on this, and we might get to like a topic or two in modern physics at the end. Okay, but this is the general idea of what we're going toward from this point on. So, keep in mind, we're studying 17.1 today. We're studying 17.2 tomorrow, only the beginning of it. What we do today and tomorrow will be on your test. We're going to review on Wednesday, don't forget. Okay? So remember these ideas. Today, 17.1. Tomorrow, we're only doing part of 17.2. But those 2 parts will be on your test on Thursday. Okay? So the 3 objectives are, first, we're going to take a look at the properties of electric charge and where it comes from. We're going to differentiate between 2 things. One is called a conductor, one is called an insulator. And you've heard these before, I assume. Maybe in middle school science. If not, no big deal. We're going to start from the beginning. And third, we're going to distinguish among ways of charging. Charging by contact, charging by induction, or charging by what's called polarization. This term here is the same spelling as the word polarization when it comes to eyeglasses that we studied already. They are different though. They are different things though. So keep that in mind. On the test, when I ask about polarization, if I ask about polarization and electric charge, it's this. If I ask about polarization and light rays, it's the polarization we talked about in chapter 14. They're the same term, and you're going to see this a lot in science, that you have the same terms over and over again in different fields. Okay, so don't confuse the two when you see polarization.
Is this like thermal energy?
No. Thermal and heat and thermodynamics I already recorded the video for, in addition for your subject test if you're taking an SAT.
Oh, I thought it was like conductors and insulators.
It's the same idea. Same idea, like conductors in thermal conduct heat. Insulators are like a coffee cup that keep the heat in or don't let heat go through. Same idea, but with electricity. Same terms though, but just electricity going through.
Oh, it's like you see like a rubber thing around you, like,
Yes.
Isn't it like plus and minus or something like that?
Yep.
I remember doing that in
We're going to talk about positive and negative charges. Very good, okay? So a lot of this you might recall this, but we're going to make believe everybody's starting from scratch. Okay? So we start from the beginning. There we go. So first, let's write down our definition of electric charge. And this is my definition. Your book doesn't give one, but I really wanted to define the term because it's something that we're going to use a lot. So simply put, it's when a material has more electrons or fewer electrons than in its normal state. That's all it is. When there's more or less electrons than it should have. Now, if there are more electrons than it does have, it's negatively charged. Because electrons have a negative charge. If there are fewer electrons than it has, it's called positively charged. Because it's missing electrons, so it's got to be more positive, or an abundance of positive charges. Okay, then it's in normal state. Now let me give you an example real quick. Okay, let me give you an example of this. So imagine there's going to be some stuff where we're going to make chemistry references, like we're going to talk about things like ions, but we're not going to go into the chemistry behind it, but we're going to talk about and use those terms, okay? So you're going to hear those terms, yes. So if you think about a simple atom, right? You know, we drew the atom where we had the nucleus, and the nucleus has these positive charges, and it's got these neutrons in there as well, and then around the outside it's got these negative charges. So this is a helium atom right here. Okay, because there's 2 protons, which give us the atomic number, 2. So, in this case, this is what we're seeing. And notice that what happens here? What happens if this happens? Let's take a look. What if this electron just suddenly goes off into space? Or somehow it gets pulled away from it? How many electrons are left?
No.
If just one moves away.
Oh, where's the other one?
Well, there's still one, right? Yeah. So it had 2. One of them flew off or got pulled away somehow. It has 1 left. So now, if you were to balance out the positives and negatives, is there more positives or more negatives?
Positive.
More positives. See that right there? So that's why this is called a positive charge if there are fewer electrons. Okay, fewer electrons is a positive charge. But what happens if, now let's make believe that electron is still here. Okay, so the electron still is there. Make believe this didn't happen now. So now you have this amount of electrons. But suddenly, it gains an electron. Okay, it gains an electron. Now it's got 3 electrons, only 2 protons, so it's negatively charged. There are more electrons. Okay? So you're never going to see the movement of protons when we talk about charging. But what we're going to see is the movement of electrons. So when you take a comb and you brush it through your hair in the morning, and then you somehow, like, you go to move the comb away, you know your hair is getting pulled toward it. What you're doing is you're giving a charge on the comb. So there's either an abundance or fewer electrons than there should be. And your hair is the opposite. You're transferring electrons between the two. That's what causes it to stick. That's what causes your hair to give static charges on a balloon when you do this. And you stick the balloon to the wall. Okay, it's giving it a charge. It's giving it a charge. Helen?
I have 2 questions. So the neutrons don't affect it
Nope.
at all? And then also, if it, say you were to lose or gain like an electron or even like more than one, or even like a proton and it
Okay.
just became uneven, wouldn't that change
The element?
The element, yeah.
Yeah, it would actually. Now,
I
if
forget
you,
what it was called.
it becomes an ion.
Yeah,
Ion.
like an ion.
When something has the improper amount of electrons that it should have, it's polyatomic ion. Or it's an ion, but usually they come as polyatomics, meaning like sulfate or sulfite. Those are polyatomic ions with a -2 charge or +1 charge, or whatever it may be. That's because of the missing electrons.
Is there like an example that's like, I guess, like tangible for us?
Yeah, I'm going to talk about these two right here in a sec.
Wait, so what's a covalent bond?
Yeah, give me a minute and then we'll talk about it.
They share one.
Covalent it's not, it has to do with the sharing of a bond, but it's not related to this right now.
Oh, I
Okay.
thought that had to be.
All right, but you had another question. Was that it?
Yeah. Oh, I have a question. Sorry.
Yeah,
Oh, sorry, I can't see.
it's all right.
Sometimes like when my sheets are staticky, and I move my hand across it, it like sparks.
Yeah.
And like I see that. Is that because electrons are leaving it, or?
It's because there's a transfer of electrons. The direction is not necessarily, you don't know which way actually. It depends on the scenario. But like if I were to rub my feet on a carpet floor, like the math science office, every time I get up to open the door, I get shocked. I'm not joking. Because the soles of these shoes and because of the carpet or the floor, whenever I do that, it charges like your body, literally. You get like an extra charge. And what happens when you touch it, because this is a conductor, and we're going to talk about that in a minute, it grounds it. So you have that transfer, and that's what the spark is.
Like in Family Guy, when Peter like rubs
Yes.
his feet on the
Yes.
floor and then says,
That's exactly right, yeah?
yeah.
Helen?
What about, is this the same as like on the slide, on like a slide at the car?
Yeah,
When
yep.
you just keep getting shocked?
Yep.
Why does that happen? Because you...
Give me a minute, because to answer that, we have to talk about the rest of the lesson. So I will get back to these questions. They're good, but there's a lot more to it.
Is this like an example of chemical engineering then?
There is chemical engineering involved, absolutely. This is mainly electrical engineering now, because we're going to study electricity and magnetism. But there's chemistry involved in everything, so there's going to be involved. Okay, but generally speaking, we're going to study electricity and magnetism, but I'm trying to teach you guys what's happening on an atomic level, so you know what's going on. And then we'll start looking at like circuits and stuff. Okay? Now, the examples I put in parentheses, spray paint and hair products. Just to give you a quick example. If you've ever noticed a car, the paint on a car is very nice. It's smooth. It doesn't look like a person actually painted it, right? It's using spray paint that is negatively charged ions. They purposefully charge the spray paint negatively. Then they charge the car using induction positively. So when it sprays the spray paint, it automatically grabs on because of the electric attraction. And that's why, like, if you spray paint an object, there's a bunch of leftover behind it, right? You put like a board down or a sheet of paper and you go to spray paint something, there's a bunch left over behind it. But when you go to a car industry and you see the assembly lines and they're shooting spray paint, there is no excess spray paint anywhere because of the charge, because it's negatively charged spray paint, and because of the positively charged metal on the car, it automatically sucks right to it. So there's nothing that's like on the side of it anywhere. It's not losing any of the spray paint. It's minimizing the waste by using electric charges. Same thing with hair products. Ladies, you wonder why like hairspray works and stuff, and it like, you spray hairspray and you don't get a lot of it on your face sometimes. You ever wonder that? It's an aerosol. Usually you try to aim well, right? But you ever think about the fact that like the spray paint isn't like going all over, or the hairspray isn't going all over you? It's because a lot of those hair products are charged. They're charged positively because hair is a natural negative charge. So it automatically tracks your hair. And that's the reason being.
Maybe like, okay, so I used to like cheerleading or whatever, and then when they used to like spray on, like, and stop, it would go on the sides and then like it would like stick and then be like white afterwards. I don't remember if.
That means that either, one of the two options. It wasn't hairspray that happened to have that makeup, that chemical makeup that I'm talking about, or you just have really bad aim.
Oh, okay.
Not you, but
I
they.
thought that had something to do. Alright.
No.
Wait, so the cars at like on the assembly line, if it is like, say the car ends right here and the paint goes right here, does it literally
Yeah.
goes? Oh
I
my
mean, the
God.
machines are good enough that they're going to turn off the spray paint at the right time and stuff, so it wouldn't happen. But if it's off by a deviation of a little bit, it'll like pull toward it. And we're going to look at an experiment like
How
that.
much? Like kind of a lot.
Like kind of a lot, like a real lot. It's cool. Electricity is the force of electric is so much stronger than the force of gravity. You can't even imagine. You think gravity is a strong force holding you here? The electric force is many times greater than that. And that's the crazy part about it. And you can think about it by this. When you do that example with your hair, and you brush your hair with a comb in the morning, any guys use a comb on their hair? A brush? Anything? You just kind of like a brush?
I use static guard on my hair when it gets like really like.
Yeah. Well, girls, you don't want the static, right? Because it gets your hair to do like this craziness. But what you'll notice is that if you do have the comb and you're brushing your hair with the comb, and you move the comb away, your hair kind of follows the comb for a little while, right? Until it moves far enough apart that it reduces. And we're going to talk about that tomorrow with the electric force and how the electric force overcomes the force of gravity, which enables your hair to stand on its ends. Okay, so the electric force is a lot stronger than gravitational, but they're very similar.
When you're on a trampoline, you make your hair like
Yeah.
go on it, and it's like literally everywhere.
Because the electric force is so much stronger, yeah? So 2 things to write down aside from this as notes. First, opposites attract. That's why the atom is able to stay together. You have a positively charged inner core and this negatively charged outer valence electron set, so they're able to pull each other to keep it in, as one. So opposites attract. What do likes do?
The what?
Likes repel. Good. So opposites attract and likes repel. So if you have a positive charge next to each other, they're going to push apart. If you have a negative next to each other, they're also going to push apart.
Like batteries.
Yes, just like batteries. It's only when you have and magnets. It's only when you have opposites, a plus and a minus, that they attract one another. Okay, Helen.
Can I bring my zingers tomorrow?
Your zingers.
You know those things that like attach? They're silver, and you throw them up, and they go like.
Sure.
Okay, I'm gonna bring them.
Bring them and show me. Show me first.
Electricity.
Show me first. Second thing to write down. Second note is that electric charge is conserved. Meaning, like mass was conserved, we talked about, electric charge is conserved, meaning if I lose electrons on the brush that I'm using, they have to go somewhere. They don't just dissipate. Okay? Charge is not created nor destroyed like energy. Remember conservation of energy? The total energy is consistent throughout the process. Same idea here. So if the comb loses 3 electrons, they got to go somewhere. They go to your hair. So now your comb is positively charged because it lost electrons. Your hair is negatively charged because it gained electrons. That's why when you put them near each other, it causes your hair to stand up. Okay? Because you're charging one positively and charging the other negatively, which is causing that. They're attracting each other.
Oh wait, but then it fades, so does it go into like the air?
Well, it fades eventually, so they come into back what's called equilibrium. Eventually, they'll balance back out.
But they're not going nowhere. Where do
They
go?
they get
Where do
grounded
once
usually.
your hair goes?
They usually get grounded, but I'm going to wait a minute to talk about that because we haven't gotten there yet. Okay? Is the fact that electric charge is what's called quantized. Quantized means that it comes in certain levels or packets. Quanta means packet or amount. Okay? This? So it's quantized, okay? So the idea is this. The experiment that this person performed, who's Millikan, that's his last name actually, he performed an experiment where what he did was the following. He had spray from an oil gun spraying into this chamber. The chamber was separated with a slit in the middle only. This little gap right here. Okay? This little gap right there. Now, what happened was he charged the oil positively, okay, or negatively, using friction, using a particle accelerator. Okay, a little more than what we know, but yes, it can be done for sure.
We have one of those at this school.
Those exist in rarity among the earth, so we don't have one though.
You should invest in more.
Right. Got a few billion to give me, then we can do it.
Stop your bagel.
So, what the scientist did was as follows. He charged the oil with negative charges. So there are a bunch of oil droplets coming out or getting sprayed out into this chamber. And naturally, it was like a gas or like these droplets. So the gas and the droplets automatically fell. So the charges, see these positive charges, they're on the bottom of the plate. So make sure you emphasize that. They're below the plate. So these charges or these oil particles fell through this opening. But because the bottom side of this plate was charged positively and the oil was charged negatively, it caused it to come back up. And it caused it to loop back up. And you kept seeing this motion. And then it looped again. And what's happening is they were kind of hovering in the air. The oil particles were able to hover because the fact that gravity was pulling them down, but then positively charged plate was pulling them back up. So it kept going through this like cycle. And this made Millikan understand or realize that, okay, particles can be charged, and they can be charged negatively or positively. And it gave him the idea that they're charged at certain levels, which is where the idea of an electron and proton actually came from. Okay? And I'll talk more about the charge in a sec.
Is there like a video of that online?
There might be.
I'm trying to
There might be.
figure out what it looked like.
The oil was falling through,
No,
the
but
droplets,
there was,
and they
a
were getting
plate,
pulled back up.
Like, was it on the ground, like right here or something?
Where was what?
Like the plate. Like what height was that at?
Doesn't matter. It was at some height above the ground. This is a chamber. This is a chamber with a plate in the middle of it with a little opening. And it wants to fall to the bottom of the chamber because gravity pulls it down, but the electric force here keeps pulling it back up, and then it falls down, then back up. And it was continuing.
So the charge of the plate was like almost equal to gravity.
Exactly. It counteracted gravity. Exactly.
How do you negatively or positively charge something, or are things just naturally like that?
She asked that question about 2 minutes ago. If you want to charge something specifically, like oil, for example, it's done by usually with friction, okay, but it's on a molecular level. So it's a little bit more complicated than what we're even going to do here. But you use like a particle accelerator usually.
But it's like an actual like process.
Yeah, it's not like it just happens suddenly, no. Okay, but we'll talk about charging things by means of conduction, by means of induction, and by means of polarization in a minute, and that might help with that idea. Now, the gist of this, what he really gained from this, was that elements can be charged, but charged at certain levels, and this is what I'm getting at here. So for example, elements have a natural charge, and the base charge is going to be what we're going to call E. Okay? And E is approximately 1.6, and I should write the approximation symbol. Okay, it's approximately 1.6 times 10 to the negative 19, and this C stands for Coulomb.
Cooling.
And it's actually spelled with a lowercase c, but the abbreviation is given a capital C to avoid confusion with the speed of light, which is a lowercase c. Again, it's spelled with a lowercase, but the units are a capital C. Because a little c makes you think of the speed of light, the number that we've been talking about, 3 times 10 to the 8 meters per second. So we use a capital C for Coulomb, but the spelling is lowercase here. Now, the value E is where protons and electrons actually get their charge. That's the quantity. So, to give you an example, a proton is simply the same thing as E, but it's positive E. An electron is just negative E. So if you were asked, like, what is the charge on a proton? It's this number here. What is the charge on an electron? It's negative 1.6 times 10 to the negative 19 coulombs. Okay? And we'll talk about this more in the next section, 17.2, how this turns into forces, and how we can compare the force of electricity and the force of gravity in newtons. For now, just write this down. This is your standard charge, okay, for a proton and an electron. A neutron, what might you assume its charge is? Neutron.
Isn't it a negative thing? Positive and negative?
So what is it?
0.
There you go. Okay, a neutron is zero charge, or neutral. Hence the word neutron, all right? Neutral. Because it consists of a positive and a negative that attract each other inside of the neutron. So the overall charge of a neutron is 0. Okay? 0. All right.
So is there a charge between two objects also?
If
Like the hair and the brush, is there a charge between them?
there's a force between them. There's no charge ever between stuff. There's a charge on the comb and a charge on the hair, which could cause a force to act between them.
Okay.
Okay? But the charges are on the individual objects.
Can cause the charges to change.
You can induce a force field, which will change the charges. Yeah. Okay. Everybody loves that. It is a real thing, I know. All right, 2 things to talk about, 2 terms. The first term is insulator. The second term is conductor. Okay, insulator and conductor. They're opposites of one another. And as Helen said a minute ago, it is very analogous to heat transfer. Okay, same terms. It just has to do with heat as opposed to electricity. So an insulator, okay, is a material that does not transfer charge easily. Okay, it insulates something. For example, rubber or glass or plastic. You can't send electricity through those things usually. They don't transfer charge easily. As opposed to a conductor that transfers charge easily, which is most metals, for example. That's the easiest way to think about conductors, most metals.
I have a question. So you know how in the subway the tracks are like electrified?
Mm-hmm.
If you were to like fall onto them
Mm-hmm.
with shoes, you wouldn't die?
Only one track's electrified.
Yeah, only the third rail is, first of all.
That's a myth.
No.
Is it?
Yeah, that's okay. Eddie Curry, his like uncle did something, and it could have been Eddie just messing with me, but I like fought him on it, and he was like telling me about it, and he like
Okay.
seemed like he knew what he was talking about. Apparently, it's a myth. It's just like the way I don't know what I'm talking about.
No, it says on the subway like
I don't know. That's what.
Well,
Eddie
maybe more than just the third track, but
Yeah.
it's definitely electrified. I can tell you that, because that's how it gets its energy. And your question was, if you stepped on it with your shoe, because your shoe is rubber, would you get electrocuted?
Well, it's such a little amount of rubber.
Well, yeah, I mean, it might. I don't want to say yes or no,
It wouldn't have
because I don't know the
been-
exact answer without actually trying it. I'm not going to try it.
Yeah,
Yeah, I'm not trying it. I can look it up.
No, I feel like it would minimalize it, but you would still be shocked because it's like what?
Wait, is that why like electricity from the wall has a rubber thing around it a lot? Like those thick electric wires, they have like a rubber.
Of course, absolutely. That's exactly why. Why are wires rubber on the outside? Because rubber is a natural insulator. So when you touch a wire, like when you touch this wire right here, take a look. There's electricity flowing through this wire right now. There's electrical charges going through this wire. I'm not getting zapped because of the fact that there's an insulator around it, this rubber. Now, when I open it like this, what happened is the circuit is no longer existing. So there's no electricity anymore. So I can do this, and I'm not getting zapped because of that. Because the circuit is not closed. Okay? But if you had some sort of electrical plug plugged in, and there was not rubber around it, or if the rubber was fraying, you can get zapped. Okay, you can get zapped. I got zapped the other day. I was trying to fix an electrical wire in my house. Yeah, you can get zapped as well.
I've done
You can. Maybe not like your finger, but if you take, don't do this obviously, but if you take a metal object and you were put in an outlet, you would get zapped hardcore. When I was younger, I got zapped real bad. My uncle was redoing our basement, and he left exposed wires, and he left them live. He didn't turn off the circuit in the house. And I walked downstairs as a kid, and I went to I think I was getting cereal or something from the cabinet, and I walked by and touched it, and I got thrown away, thrown to the ground because it was that strong. Yeah. No. I think that one might be a myth too. Helen.
Okay, so a few weeks ago I was at my cousin's house and they had an exposed
wire,
outlet, and I put my plug in it and I got zapped so bad. But it was looked fine. Is it just because it was so, I don't know.
I don't know. I'd have to see it to give you an answer. I'm not sure.
Wait, what about when you put I'm gonna make this one. If you put something in, a plug in an outlet and then you take it out and you touch it right after that, you do get zapped. That's happened to me before when I was
It might be holding a static charge.
Is it because it transferred into the metal?
It's possible. I'm not sure. I don't know what kind of a zap we're talking about here. When you unplug from an outlet, have you ever unplugged or plugged in an outlet? Sometimes you see a little spark. You see that little spark there? Yeah, that's the completing the circuit. It's automatically sending it through, and there's a little bit of induction going on there. But electricity is an interesting thing. It depends on the scenario. Chess.
You get zapped if it's also a big battery too, stuff like that.
No, but if you take a D battery where it's got the 2 nodes on the same end and you touch it to your tongue, it will start flowing the electricity through it, and you'll feel like a bit of a burn almost, or like a bitter taste.
Sometimes the batteries don't work like either ends.
Yeah, I wouldn't do that.
I do that all the time, and everyone thinks I'm so weird, but it works. Looking
I
tastes so good.
Oh God! Don't do it, Thomas.
There was a kid in my old school that he had to pee, and he peed on an electric fence, and the electricity traveled up
Through the urine stream into him? Did he die or did he?
No.
Okay.
That's
Yeah.
hilarious.
Well, water is a conductor of electricity also. That's why when it's lightning out, you shouldn't be in a pool, ocean, any of that stuff, ever. Okay? Bodies of water are natural conductors.
Some kid in my pool club got electrocuted once because he was like, he was so stupid. He was like standing on the sidelines. He was like, oh, nothing's gonna happen, and like he put his foot in the water, and then a lightning thing came.
Yeah.
It was fine though, but.
All right, we got to keep going, guys. We're not even halfway done, and we have 2 minutes left. Listen. Now, the next type of conductor is a semiconductor. Okay, and what you should know about a semiconductor is that it's naturally an insulator. It's naturally normally an insulator, like silicon. It's normally an insulator. But with the addition of the right atoms, it can become a conductor. So a semiconductor is not something that sometimes conducts, sometimes doesn't. Like, pick and choose. No. It's if you add a certain, I guess, set of atoms or specific set of atoms, it causes it to become, unbalanced, and which enables it to become a conductor. So a semiconductor is something that's normally an insulator that can become a conductor. A superconductor.
Wait, so a semiconductor is insulator if you put electrons in it and it's a conductor? Sorry.
A superconductor is certain metals that become perfect conductors when they're below a certain temperature. And that's what we talked about quickly when I mentioned about computers that time. And I talked about how you can, and this is in your video for thermal that I recorded online also, but you can what's called super cool computer. You can overclock it. If you cool it down enough, it transfers energy and electricity faster, okay, and at a better rate. Yes.
His like has a freezer attached to it. It's like
No, but he likes it.
It's a metal that becomes a perfect conductor under a certain temperature. Next. Charging by contact. Okay, charging by contact. We're reading my notes. You can get them online. Charging by contact. I have notes for myself here that I need to read as well. First, there are several things. Charging by contact can happen easily with an insulator, and that example, the example of charging by contact is usually when friction is involved. For like when you take the rubber balloon and rub it across your head, what you're doing is you're charging the balloon with one charge, so a lot of electrons are maybe moving from your hair to the balloon, and your hair is getting charged by the other charge. Okay? So if one is positive, the other becomes negative. So what you should write down here is that an insulator can easily be charged by contact. An insulator can easily be charged by contact. Now, a conductor, though, is a different story. And the issue is this. If you try to charge a conductor, for example, if you were to, let's say you had a charge on a comb. So you rub the comb to your hair and it creates like a negative charge on the comb. If you were to touch the comb or put the comb near something else that's an insulator, it can transfer that charge on the surface. But if you touch it to a conductor rapidly changes charge or moves charge. So if I took that comb and touched it to this metal podium, the charge is going to dissipate over the surface of the metal and it'll pretty much get grounded into the ground. The earth itself is like a giant conductor of electricity. So when you hear the term something is grounded, it's like a lightning rod. A lightning rod on the side of a house is this giant metal rod that causes lightning to hit the rod and not the house because the metal attracts the electrons. And it takes and it goes through the lightning rod into the ground. So it grounds it. It sends the electrical charge into the ground. So with a conductor, if I'm holding a conductor, let's say this metal, okay, and I have something that is charged negatively, and I go to touch it to it, it's going to go through the conductor into my hand, through me into the ground. So it's not going to hold the charge, a conductor. A conductor needs to be held with like rubber. So if I were wearing rubber gloves and I held the conductor, and then I put a charge to it, it'll stay charged. But if there's some sort of other thing that can transfer energy, it's going to transfer through the conductor, through the entire surface of it, and into my arm, into the ground. As opposed to if I'm holding this plastic pen, and I'm able to charge it, the charge is not going to flow through the plastic pen into my body. It's going to stay on the surface of the pen. Okay, so it's easy to charge an insulator by contact, But to charge a conductor by contact, it's much more difficult because the conductor wants to send the electron into the ground or send it through into the next body.
Is that why, like, when you're making like glass or something, or like the different things, you can put
When you're making glass?
or like not like glass, but like sand. Have you ever seen Sweet Home Alabama?
No.
They like put like a lightning rod in it, and like when it's like lightning out into the sand, and then when it hits it, it makes like
Sea glass.
it makes like sea glass.
Oh, well, I think that's just, so the lightning's coming through the rod, through the metal.
And then it goes into the sand, and then like when like it's all over, you take it out, and it makes like a kind of sea glass.
Well, the abundance of electrons are going to cause like it to melt. That's what's happening there at the bottom. So it's going through the metal into the glass, and it causes the glass to actually shape or melt. Yeah, I mean, but the metal rod, the idea is that it's attracting, yes. It is attracting. I didn't know if that was in a movie.
Wait, you said like glass is a like insulator?
Insulator.
But my friends, like my best friend's mom, their living room was all glass and it was lightning and she was laying on the couch and she got a lightning pin from lightning. So I like put it through the glass.
It must have been something else that happened,
So
but the glass is a natural insulator, yeah.
Really? So it would never go through a window?
I mean, it could hit the window for sure and it would destroy it, but...
She was laying on the couch. My house got
Listen, I'm going to record.
and it went through a window.
I'm going to record the next like 10. Okay, so induction is an interesting process that involves no contact. And what we're going to see here is that induction is the process of charging a conductor, but just by bringing it near another charged object and then grounding the conductor. But you're never going to touch it. So let's take a look at the example here. So imagine you had a rubber rod near a piece of metal. Okay, a conductor, metal. So there's a conductor here. This is a piece of rubber, like a rubber rod. And the rubber rod is negatively charged. The minute you bring the rubber rod near the metal, it's going to draw the positive charges toward it. So what's going to happen is it's going to cause the charges to separate inside of the metal conductor. Then what you're going to notice is this. After that after that scenario happens, after this first case here, you can then attach the conductor to some sort of a grounding element. You know, simple as like a human being will ground the charge into the ground, or say another piece of metal to ground it. And what happens then is that all these negative charges that were separated actually flow into the grounding wire, into the ground. But because these positive charges are held here because of this negative rubber, when you remove the grounding, so we cut this now, so we remove the grounding somehow, and we're left with this scenario, where all of these positive charges are still held here by this negatively charged rubber rod or whatever it may be. And then once you remove the rubber rod, you end up with a charged conductor. So this is called charging by induction. Charging by induction. The last thing to look at is charging by polarization, which has to do with an insulator's molecules realigning itself. So they're not necessarily separating like we talked about with the conductor in the last example, but in this case what we're doing is we're seeing this. We're seeing, imagine if you have a comb, all right, and you bring the comb to your hair and you strike it through your hair, it becomes charged. So let's call this the comb right over here. Okay, the comb is charged. Now, the charged part right here, naturally, if it's positive, draws the negative parts of the molecules or atoms inside of the insulator. But because the insulator does not allow flow of electric charge, these are not going to separate much. They're just going to become what are called poles or polar. That's why this is called polarization. So the negative poles are all along the surface of the piece of paper because of the comb that is positively charged that draws the negative charge toward the surface of the paper here. So the comb is able to pick it up because it causes polarization and these induced charges. Okay, so it's like another type of induction, but we call it polarization. We're not looking at a conductor anymore. We're looking at an insulator where it forms these dipoles, okay, where there's two poles, one on each end, and these lines are all arranged so that the paper is able to get picked up by the comb. Again, though, it still has no net charge, the insulator. It has no net charge. This is not like losing a charge like it did with the example of induction, where it lost all those negative charges and it only had the positive charges in the end. This is just a realignment so that the surface has a certain charge. And again, no contact involved. Your homework is 633, numbers 1 and 3.